Hi, it's Dahlia Remler, and I'm back with the next part of causal research where we're going to take the causal theories that we were learning about and we're going to be able to use them to create better causal evidence with observational studies and also to assess the causal evidence that other people create. So the general approach is observational studies with control variables. As you know, observational studies are those where we just get the data by looking at the world and we're not interfering with it. So let's look at the opening example in the book. Are private schools more effective than public schools? Which is obviously of very big interest. So private school students have higher average test scores than public school students do on the National Assessment of Educational Progress, or NAEP test, which is often considered the gold standard for description. It's considered to be valid, reliable, consistent across years, and less subject to political interference. And in 2008, private school students had an average score of 237 on reading compared to public school students with an average score of 218. So that's a 19-point gap, and it was statistically significant. And many people interpret results like that to mean that if we only sent the public school students to private schools, perhaps providing vouchers or so on, they would do better. And you'll recognize that as a counterfactual question. What would happen to the public school students, that's the factual, what we have now, if they went to private school? You can also think of it going forward as a potential outcome. We have a bunch of young children who haven't gone to school anymore. We can envision two potential future roles, one where they go to public schools, one where they go to private schools. But it's observational data. We're just observing the world. We're observing correlations and we're trying to infer causal relationships. And as we discussed, correlation is not causation, which everyone loves to say, but they often don't apply rigorously. And so we want to figure out, does this correlation, which is very strong suggestive evidence, you don't want to just dismiss, does this correlation in observational data, naturally occurring data, provide good causal evidence? Because people are making choices. The type of school that a child goes to is dependent on their characteristics, their parent characteristics, choices they and their parents make, choices that the school makes. It's endogenous. It's driven by the same kind of variables that affect their test scores anyway. That's in contrast with experimental data where like some outside administrator or scientist just says, you public, you private. So what are we going to do? What's the essence of control variables? The essence of control variables is to try to make apples to apples comparisons, to try and make this, that in our statistical analysis, that the students who go to private schools and the students who go to public schools are going to be the same in relevant characteristics. In reality, the students who go to private schools differ from the public school students, most obvious being things like family wealth and income, can be religion to some extent through Catholic schools. It can be families' tastes and interests in the students, all kinds of things. So the problem is it is all kinds of things, because the idea of the control variables is the study is going to use control variables to make a fair and equal comparison. So there was a study done with this 2008 NAEP data, and it used control variables to basically compare private and public school students who were essentially the same in whether or not they had a computer at home, free lunch eligibility, Title I participation, which indicates economic disadvantage, books in the home, English language learner, and some more variables too. When they did that, the public-private school gap fell to 0.10 points, no longer practically significant, and not statistically significant either. So now we're going to go more in depth with a specific empirical example looking at higher education and higher earnings. People think that if you get more education, you will earn more. Why do they think that? Because they observe that on average, those with more education do earn more. So they're jumping from correlation to causation. Now, how do you get convincing evidence? And later on in the course, we're going to talk about a bunch of other methods, randomized experiments, quasi-experiments, natural experiments. But these things aren't always possible. Sometimes they're expensive, sometimes they're unethical. So we're going to continue with observational data, naturally occurring data. So here, this is the same example in the book. We've taken the National Longitudinal Survey of Youth, the 1979 version, and we're looking at people, which means it started when they were like 14 then, and we're looking at them at 2002. And what do? We observe that those with a college degree earn more. In fact, on average, $32,000 more. So sometimes people look at this and they say that's the effect of college, effect being a causal term. The college degree caused the higher earnings. Or the return to college, how much more do you get? But that's not right. People self-selected into different levels of education, and other people selected them in a biased manner based on their characteristics. And when we say select, it doesn't mean it's like some choice that's purely driven by their preferences. No, selection can be because, hey, my family has no money, I have to support them, I have to work 70 hours a week to earn enough money, so therefore I'm not selecting college. The key question is whether those factors that drive college degree could independently and separately drive earnings. In other words, is it a common cause? And our goal is to create, in essence, these comparable groups. What we're going to do is we're going to estimate the effect of a college degree by looking at the earnings of people with a college degree and a whole bunch of relevant characteristics like their family's income and wealth, things like that, and compare it to the earnings of a group of people without a college degree but all the same other characteristics. So, we're going to control for all the relevant confounders. That's the idea. And I want you to focus on the idea for now more than like the statistical methods, which all have their own pros and cons. Just the idea. And also, for now, don't worry about how are we going to know that we have all the relevant characteristics. That's really hard. We'll spend a lot of time on that. But for now, just focus on the general idea. So the control variables concept is find all possible common causes. We're coming back to that. Using theory, common sense, other evidence, look for things that are correlated with both independent and dependent variables, but that's not enough to make them good controls. Again, we'll come back to that. Common causes are the desired control variables. Then what we're going to do is we're going to compare outcomes that differ by treatment, like the college degree, among those with the same values for common cause variables. So step one, really I should have said step 0 is to see if your independent and dependent variables are correlated. If they're not, there could be a causal effect, but it's much, much, much less likely. Like the true effect and bias would have to just cancel. It could happen. Once you've done that, the control variables method is first speculate on common causes. Focus on what's driving that independent variable. Why do some people go to college and other people don't? Could those same factors drive their earnings separately? Then look for differences. Look, how do those people who go to college and the people who don't go to college, how are they different? Then, when you've got that, you select your control variables using both the empirical differences and your common cause theory. You make those your control variables. And for now, the statistical method we're going to use is the simplest one, stratification. You stratify by control variables. So, finding common causes of education and earnings. Step 1. Already talked a little bit about that, but clearly a really big one is the family's socioeconomic status, their income, their wealth, the parents' education, which both helps the students with their education and also creates a cultural norm about going to college. All of those things will also have driven the early college education. The empirical setting I showed you started data collection when the people were 14. And, a lot has happened to people by the time they're 14. There's a lot of early education quality. A lot of things have happened. There's also aptitude for learning or interest in learning. All of those things go into early achievement because we also have to worry about how we're going to measure these common causes and get a proxy for them. And then what we're going to use is their score on a test, the AFQT test, when they were 14 years old. So we think of that as a measure of early achievement that's really reflecting a lot of these common causes that we have. So now we're going to step 2 and we're going to compare, we're going to look at the relationship between our independent variable, college degree, no college degree, and a bunch of potential common causes. So you can see this is not an apples to apples comparison. The students with a college degree were 7 points less likely to have had their families be in poverty when they were children. They're 20 points more likely to have a mother with a college degree. Almost 20 points more likely mother is professional technical worker. Oops, sorry about that. There's race and ethnicity differences. And a really big one is this early achievement score. There's a difference in 34 points on how they did on this test when they were 14. And a lot of different stuff has gone into that. But that kind of stuff affects whether people go to college, and it will also, your early childhood education and the things which drove it will affect your earnings separately. We're going to, for the purposes of stratification, make this score variable into a dummy variable, a dichotomous variable with 2 characteristics. This group, the high score, are in the top third of the distribution. This is in the bottom third of the distribution. And again, you see a big difference. So for now, to just teach the method, not to get a good estimate, but to give you the idea of the method, we're going to pick one possible cause, this early achievement, and we're going to make it a categorical variable with the high score being the top third, and then we're going to stratify by early achievement, by test score. So if are they a high score or not. So remember from sampling, stratification means to separate into these exhaustive and mutually exclusive groups. So everybody's in one and only one groups. We're going to break them in the groups, and then we're going to do our comparison, look at our relationship within those groups. So now you see this here. What you see is with both groups combined, the difference, the effect, which is in quotes because it's not a very convincing effect. For the high scores, that's down to 27.8 thousand. For the lower scores, it's down to 18.7 thousand. So these are our new estimates where we've controlled for early test score, early achievement, in the simplest way possible with stratification. So now we have these two estimates. They're both lower than the original estimate. So you can see the estimated effect of education is reduced. It's gone from 32 to 18.7 and 27.8. So we say this was biased due to the common cause. When we failed to control for it, what we estimated was too high. When we did control for it, it went down. So without the control, it was overestimated, too high, upwardly biased. When we talk later about predicting the direction of bias, that's what we mean, saying something like that. There's also an interaction where the size of the effect of one variable, the size of the effect of college education that we're estimating, depends on the value of the other one. So that's very important. We discussed that with moderators when we did theory, but right now we're focused on just the bias. So what's still missing? Well, what isn't still missing? So first of all, the test scores vary within the test score group. It's a continuous variable, a quantitative variable. We're going to solve that with regression. Secondly, we had all those other common causes. What about them? We just did the one. So we still have bias without all the relevant controls. We need all of them. So what if we try to do all of this with stratification? Oh my God, how many different multiple layers of comparisons do we have? It might be possible, but unwieldy. We also have this problem that the different cell sizes get too small, and that's solved with multiple regression. So we're gonna come back to general principles about choosing control variables. But first I want to talk about what you do if your dependent variable is categorical rather than quantitative variable like earnings is. So what we did before was we did a comparison of means, a difference in means because we had a quantitative variable, and then we stratified that. Well, what do we do if we have a categorical variable? We would do a crosstabs potentially for the relationship first, then we're going to stratify that. So let's look at this example of that I should have put that it's from, I think, Muzio and Van Ryzin, Greg Van Ryzin being my textbook co-author. At the height of the push for broken windows. So this is old data, but it's very topical now. So the variable we're interested in is people's responses to whether the New York City police feel that whether people believe the New York City police are generally fair in the way they handle people. And we're looking at this issue about whether income seems to affect that. And again, this is just a descriptive relationship, but we're interested in whether it might be causal. So we have this crosstab. We're looking at the difference between people who earn less, or households that earn less than $35,000 and those that earn more than $35,000. And you can see that there is a difference, right? So basically, the higher income group is 8 percentage points more likely to say yes, and the 7 percentage points less likely to say no, 1 point less likely to say they don't know. So we see there is a descriptive relationship, a correlation, if you will, an association more rigorously, between income and perceiving police as being fair. Is that really true? Is that the underlying cause? Maybe police are reacting more to race, ethnicity in their handling of people. Maybe that's the larger factor in fairness. And of course, for a long variety of reasons, historical legacy and many reasons, we know there's a difference in earnings by race and education. So now we're going to use the same control approach. We're going to stratify by race, ethnicity, and we're going to do it in the simplest possible way. We're going to do white, which is actually white non-Hispanic, and non-white, and we're just going to stratify that way. So basically we're doing exactly the same analysis, but separately by these two race ethnicity groups. So let's look among whites. Is there a difference by income? It's 0.3 percentage points, and I didn't put the chi-square test and the statistical significance, but it's not. Let's also look among non-whites. Well, there is some effect. There's a less than 3-point difference, but it's much smaller than what we had before. So what we see is that when you control for race, the relationship we saw with income goes away, suggesting that income might not be actually the driver of perceptions of police fairness. I also want to talk a little bit about language. We've mostly been using the term omitted variables bias. That's bias in a regression or other statistical analysis due to failure to include or adjust for important common causes, omitted. That term comes from economics. It's popular in economics, now in program evaluation, and we like it because it kind of says exactly what it is. A much more common term is confounding. So again, that there's a distortion in some correlation, measure of association, again, the idea of using that of a causal effect between two variables due to a third variable, typically a common cause that is unmeasured or unaccounted for. Confounding is a very common term, medicine, sociology, psychology, public health, very widely used. You'll also hear spurious effect, but that has a narrower meaning than omitted variables bias and confounding. A spurious effect is when the true effect is 0, and the one you're estimating is entirely biased. There's also the term treatment selection bias. People use that because, again, the idea is that the treatment, the independent variable, the thing you want to know the effect of, is biased. Like how people get in one group or another, or how people have different values for education or whatever your independent variable is, that's not random. It's driven by things that drive the dependent variable, or for reverse causation, driven by the dependent variable itself. You have to be careful with that term selection bias. Remember, we already had sample selection bias. And you have to be careful because in some contexts, in some disciplines, when people say selection bias, they mean sample selection bias. And they don't say it, they know it, that's what they mean by it. In other contexts and disciplines, when people say selection bias, they mean treatment selection bias. So you got to sort of look at the question and know what people are talking about. Now let's return to what's really the most important issue here. How to choose control variables. First, let's start with some general principles. You want all the common causes. It can be hard to get them. We'll come back to unmeasured variables and what you do about the fact that you can't get them all, but you want all of them. Secondly, and this is really important, just because someone uses control variables of some kind does not mean that the results are unbiased. There is no standard set. Depends on the question, depends on the setting. It's got to be the right controls. Another important principle is that you don't just throw in everything available. Adding some controls can make things worse, and we're going to get to that. So just, you might think, oh, let me throw everything I have at it. The old kitchen sink, they used to say. Nope, don't want to do that. You're not always going to get your common causes that you want, so you're going to often have to look for proxies of them. So path diagrams are really, really clear. Look for common causes. Use your common sense and imagination. Path diagrams are what are increasingly called causal diagrams, and a rigorous form of them called DAGs, or directed acyclic graphs, are extremely valuable, and you really want to think through these causal relationships clearly. Like I said when we were doing the theories, with the logic models, with the mechanisms, and when we were using path diagrams to look at non-response bias and so on, take those arrows very, very seriously. They mean if you take the first variable and change it, the second one changes the result. This is not a time for vague thinking. Arrows go away from good controls. They go to both the dependent variable and the independent variable separately. This is the real work of control variables method. And to be honest, even if you're not planning to become a researcher or an analyst, this is the real work of being a good consumer of other people's research. This is key to not getting duped or misled by observational studies that are trying to estimate causal effect. So let's look at our here. So we have in pink the independent variable that we think is the independent variable, college degree and earnings, and we want to know the effect. Oh, and I forgot to say, for all of you worried that I'm saying that a college degree is no good or more education is no good, don't worry. We have lots of that natural experiment evidence and other evidence that it really is. It's just that sometimes the numbers people put on it, including in newspaper articles, are inflated. Sorry, forgot to say that earlier. Okay, so now, again, we want to know the effect of college degree on earnings. So we have these common causes. We have parents' education, which influences them getting a college degree for cultural reasons, for their help in navigating things, for their help. And parents with higher education can separately help earnings. I haven't spelled it out here, but there's a network. They know other people who can help get you hired and get a good job, even if you don't go to college. So parents' education is a common cause. Early achievement is also a common cause. A lot has happened to people by age 14. They've learned a lot. The quality of their earlier education, the confidence that gives them, so on. That affects going to college, but it also has its own effect on earnings, even if they don't go to college. So we have two common causes. We want to do them. When you draw your diagrams and you do your broad-ranging skeptical thinking, you're looking for common causes. But remember, they won't always be this simple. As you saw in my words, I was skipping some variables in there, like having networks for, introductions to potential employers. I was skipping some stuff. but the main structure will be the common cause. So, what are not good control variables? Intervening variables. This is the biggest mistake that I see students make, and not just students. You see this, unfortunately, in a lot of published research by people who ought to know better. So, suppose that, again, we're trying to learn the effect of the college degree on earnings. Now, maybe you have a bunch of data, and it's very rich data, and you learn that, hey, people with better writing ability are both more likely to go to college than not, and they earn more on average. It makes sense. Writing ability is rewarded in the job market. Your problem is that this is an intervening variable. Yes, better writing ability causes people to earn more, but your problem is that going to college also increases writing ability. At least we hope it does. And if you control for writing ability, you're basically taking away part of the effect of going to college. Because it's not that writing ability drives college and earnings separately. Going to college makes people write better. And remember, we want that old counterfactual thing, a comparison between what people would earn if they went to college and what the same people would earn if they didn't go to college. But we're not getting that counterfactual if we hold writing ability constant. The non-college group are people who wrote that well, even though they didn't go to college. They would write even better if they had gone to college. Whereas the college group, they have a higher writing ability than they would if they hadn't gone to college. So this undoes part of the effect. So if you want the whole impact of college on earnings, you don't do this. Now, sometimes people do mediation analysis. So we talked about that a little bit in the textbook, and that's where they want to see how much of the effect of college on earnings is due to writing ability. And then you may want to control for it. However, that's something else you have to be careful about. The recent causal inference work, people like Judea Pearl and a lot of other people, have emphasized the problems with how that's often normally done. So what are some other complexities? Well, what do you do if the variable is both a common cause and a mechanism? Think about that writing ability. Yeah, okay, writing ability is affected by it, but also there's probably an early writing ability before college. That might help you get into college. What do you do in cases like that? Well, if you've got your regular cross-sectional data, you just got to do the analysis both with and without, see what difference it makes, use your best to have theory and kind of say, okay, this is what could be the case. Now, longitudinal data over time, that's going to help us fix things. And we'll see more about that in chapter 15. Another important thing are causes that can be ignored. And this is, again, something that a lot of quite sophisticated researchers don't quite get right. People often say, if it influences Y, I want it. If it drives the dependent variable, it's great. I need it. It's an important control variable. Not exactly. It's not, if it's not driving X or not related to X, leaving it out doesn't cause bias. Now, you might want it anyway because in some circumstances it increases your precision. Lower standard errors, narrower confidence intervals. But leaving it out won't cause bias. And again, that's something people often forget. Another really important thing is the controls depend on the question. And we haven't talked much about how when you use control variables, when your independent variable isn't endogenous, but people do that. So for example, people are interested in race or gender as an independent variable to see if discrimination exists, or to understand the source of earnings gaps by race and gender. So if your goal is to see if discrimination exists, should education be a control? It kind of depends even more what your question. If you're checking for discrimination by an employer, sure, that's a relevant control. Education is a valid thing in hiring or earnings. But if you want to know if standards of living differ by race for a variety of historical or structural reasons, you don't necessarily want to control for education. Differences in education can be the mechanism through which in effect, discrimination or structural racism is occurring. And so for those purposes, you would not want to control for race. So for education, if you're interested in looking at structural racism. So again, these things, you really have to think about what you want to know. There's a traditional view that when you've got these endogenous independent variables, how do you decide what's good control? Well, if your variable drives the dependent variable, it is correlated with the independent variable, and it's not caused by the independent variable, so it can't be an intervening variable. You're like, okay, we're golden, that's a good control. And I thought that, and it's why in earlier editions we talked about these complex and unknown common causes, as well as, oh yeah, it's really a common cause. Recent research has said, you got to be a little more careful than that. Use rigorous approaches with causal diagrams. Common causes or proxies for common causes are best. If you're interested, there's a really good online course, edX, by Miguel Hernan, who's an epidemiologist who works on causal research methods, that is pretty accessible, and you can get it for a month or maybe 2 months, some amount of time for free. Okay, so now I want to turn to this issue of how you figure out the direction of bias. So, okay, you've got a common cause, and Professor Me wants to know what's the direction of bias. And not just me, you've got in your real life, someone published some study, and you're like, oh, that's great. That really looks like that's an effective program. They're using observational data to judge that. And you're trying to, and then you say, oh, but you know what? They didn't control for, full-time student status, or they didn't control for this background variable, or whatever it is you think they should have controlled for. And you want to try and see, well, what do I think is the bias in their estimate? So how do you do that? You start by drawing a causal diagram showing the effect you want to know. Then you draw the common cause as well that you're concerned about. And again, it could be more complicated, but you want the essence of it here. Like, here's this variable, this common cause that they're not controlling for, we want them to control for. So you have to look at that. And then you look at the sign result if there was only the common cause. So forget for a minute that there's any causal effect, and imagine that all the relationship was just due to this common cause. No true effect, no other common causes, nothing else. In this case, we see there's a plus sign. That means that that's the bias. So here's like this ruler. Here it would be, here's what you get if you're not controlling for C. And it's bigger, more positive than it would be if you did control for C. So this is great. The complications come with negative signs for lots of things. So we could make this a negative sign for one of them with a negative correlation, and then it would be the other way around. Not controlling for C would be in the other direction. That's great, but what if this thing is really a negative thing itself? Then we might think of positive as making it smaller. So this is a start. This is how you want to work on predicting direction of omitted variables bias. I also want to talk to you about using causal language. Because it's so hard to estimate causal effects with observational data, researchers often use this mealy-mouthed language like it's associated. They're like, oh, me? Causal effect? Is my research? Oh, no, I'm not trying to estimate a causal effect. No, it's an association, a correlation, a risk factor. No, and my controls are just to see how that relationship changes when you add controls. That's great if that's an honest answer. But often the true goals are causal. You see it in their introduction, you see it in their conclusion. Oh boy, do you see it in their grant proposals and in the media descriptions of it. Despite that, some journals and disciplines insist on this language, medical journals in particular. If it's not an experiment, get rid of your causal language. We don't agree with that. Why? And by the way, this is what I'm going to say is what you increasingly hear in the causal inference world. If you really want to know a causal effect, and that's your goal, own it. Say it. Say it's an estimated effect, causal language, the effect of this on that. But at the same time, there's a reason all those journals and disciplines told everyone to use the mealy-mouthed language, because often, as you've seen, this is not going to be a very convincing estimate. In fact, sometimes there are no good, very bad, terrible, horrible estimates in the words of some child's book. Okay, so you don't want to overclaim their estimates, and you want to say clearly the problems with them. So because of that, we want you to describe your results in two ways. One is a rigorous, statistical, neutral description, such as the mean difference in earnings between those with a college education and those with no college education. Rigorous, unambiguously correct. And then also describe it as the estimated effect of college on earnings. Now, in this case, that's kind of a laughable estimate, of course. Okay, so thanks. That's it for the basic ideas of control variables. In the next chapter, we're going to talk about using multiple regression, which is the most common way of trying to control for multiple variables at the same time. There's actually lots and lots more methods and lots more sophisticated methods as well. But now you have the key ideas. And with the key ideas, you can look at a study and say, hey, what controls did they use? Are there ones they shouldn't have been using? Are they controlling for intervening variables? What are they missing? What bias was caused by missing those variables? So often people think that the technical stuff is the most important. Propensity scores, machine learning, etc. No, the most important thing are the ideas, the conceptual things, and your models of what's driving what.